I bet this has already happened to you. You open Google Maps, you type in a source city and a target destination, and you ask Google Maps for the shortest path in between, and lo and behold, it would find you the shortest path. How did it do it? If you ask Dijkstra, how do you find the shortest path in between two vertices on a graph, he will tell you, well, there is no magic solution for that. What you need to do is basically go over all the vertices and find the shortest path into each vertex. Then just look at the target vertex and the source vertex that you wanted to go to travel to, and this would be your shortest path. So what Dijkstra has just suggested to us is that we pin the source vertex, we pin it, and from it we go and we scan the whole graph and find the shortest path to the whole vertices on the graph from this source node. And only after we do this, we would find the shortest path to one of the nodes that we have needed. This has the benefit is that if you then travel again with the Google Maps and you try to search for another city from your source destination, then if you have applied the Dijkstra algorithm, you already have it. You don't need to recalculate it because the Dijkstra algorithm calculates the shortest path from one single source vertex into all the other vertices. And then you just say, hey, I actually wanted to go to this vertex, and it would provide you back the path to this vertex. Basically what Dijkstra is telling us, you cannot know the shortest path into a target vertex by not scanning all the other vertices, because who knows, maybe there is some super fast road like Elon Musk super fast road that would get you there much faster. So you must scan all the roads because this Elon Musk road is hiding somewhere. So you must scan all the vertices, go through all the edges into the destination node in order to find the one which has the shortest path. And because we say we need to visit all the vertices, then this means that the basic data structures that we need to hold in order to apply the Dijkstra algorithm is of course the graph. You need to have a graph representation which represents the connection between the vertices, which is the edges, and each edge should also contain the weight. How much time or how much weight do we apply, the cost that we apply into traveling from node A to node B, or from vertex A to vertex B. Then we need to visit all the nodes with the BFS, breadth first search. When we need to visit all the nodes, then we need to know which nodes have we visited. The term visit is not that clear, and I would even prefer to use a different term which I have invented, which is called source visited. Because when you have the visited array, which means you mark every node that you visit, it's not really every node that you visit, it's every node that you visit as a source node from which you calculate the distance into target node. So if you visit node A and then you calculate the distance to node B, node C, node D, then nodes B, C, D are not considered as visited. So it's only the source node that we hold in the array. And therefore the basic three structures that we need to have is the graph itself, the representation of the graph itself that we are going to traverse, an array of the visited node, the source visited node from which we calculated the path from them into their neighbors, and all the array of the unvisited nodes, so we know which source node should we continue to visit, because otherwise we would need to subtract all the list of nodes from the visited. And a table which contains from each vertex into a neighboring vertex what is the cost or the weight of visiting this other node. So you had a table. The first column would be all the vertices, A, B, C, D, E, F, G, H, all the vertices that you have, all the cities that you have. And then the next column would be the shortest path from the source. If you remember, then we said that in the Dijkstra algorithm, we have only a single node. We choose a single city, like your home city, that you want to calculate the weights from this city into all other cities. It's not calculating, at least not in this version. It's not calculating the weights and the travel distance from each city to any city, only from one city to all other cities. So on one side you have a single city, and on the other side you have all cities. And you calculate the distance, the shortest path, shortest weight, shortest cost from the source vertex, the single source vertex, which is your home cities, into all other cities. So the first column is all the vertices that you have. The second column is the distance from the single home city into this vertex. So on line A, we have the distance in the second column from A to A, which is 0. On line B, we have the distance from vertex A into vertex B. And on line C, for the vertex C, we have the distance from vertex A to vertex C. And on line D, we have the distance from vertex A to vertex B, the shortest distance from vertex A to the vertex B. So if you notice, we have an amount of rows in the table that we do our accounting for each vertex. For each vertex, we have a line. And on each vertex, we say how much time would it take from the single source vertex, which we can call A, into this vertex. And we update this as we move on our BFS. If we find that we have found a shorter distance from A into this current target node, then we update it. And we also do the accounting of from which node have we reached this. For example, if we found that the distance from A to C is 5, we also say that if this was the shortest distance, then we write also in the table that we have reached node D from A, and this provided us the shortest distance. So basically, Dijkstra algorithm is simple, because all you need to do is to do a BFS. BFS, I take it you know how to do for each node. You take all the neighboring node and visit them. Each time you visit a node, you calculate what is the minimal weight to the next node. So if I'm stuck at node D on the graph, okay, and the important thing is that we do not write the weight or the cost from D to E, if E is neighbor to D. We write the cost from the original source node A into E. So the cost that we write and we manage in our accounting table, this can mix you up, is not the cost from one node into another. It's the cost from the source origin node into any node. So if you look at the table, then the cost and the distance and the minimal distance that you would see there is the minimal cost from the source original entry. And we have these data structures, all the source nodes that we have visited, so we don't need to visit them again. All the nodes that we have not visited, so we need to visit them in order to calculate the cost from those nodes into the preceding nodes, all their BFS neighboring nodes. In the table that we have for each vertex, what is the shortest path from the source origin node A into that node, and for each such node, the previous vertex that we arrived to it from. And our procedure is this. First, we initialize the unvisited array, and we also initialize the visited array. Now that we have initialized the visited array, which contains nothing, we start from the source node. If our source node is A, then we start from A, and we initialize the table where we said that we have all the shortest distances into infinity, because we do not know right now the cost to reach each node. So we have a table, imagine a table where the first column is all the source vertices, the middle column is the distance from the source original node A, okay, and the distance would be infinity for everyone except the first node, which is A, because from A to itself we have 0 weight, and another column which is an accounting column, the third column, only 3 columns, which is the previous node that we have visited in order to reach this minimal path. And once we have initialized the unvisited array and the visited array and the table to infinity and to 0, we start visiting the node with simple BFS. So you start with a BFS, you start from the first node, the weight to the first node is 0. What is the weight to each neighboring node in BFS wise? It's simply the weight that you see, so you update the weight. Because all the other weights to these nodes, B, C, D, E, F, G, is infinity. So you look at the first phase, at the most close, the closest neighbor into the source node, and you initialize to the actual weight. Now we can mark that we have already visited the first node, so we either mark or remove it from the array, and now we need to choose another node in order to visit the graph. Which node would you choose? Because the node, first node A, which has a distance of 0 to itself, has a few neighboring nodes. Which node next would you choose to visit in order to continue and fill in the weight for the whole graph? According to Dijkstra, the node that you should choose is the node that is currently having the minimal weight. It's like a greedy algorithm. So you choose the node that has the minimal weight and you move to it. You mark it as visited, source visited, and then you go with the BFS manner and calculate the weight into its neighbors. So we started with the first node A. We said that the weight and the cost to itself is 0. Then we updated the table with the cost to all the neighboring nodes, BFS. Then we have chosen the next node from the neighboring nodes, neighboring vertices. How do we choose the next node to visit in BFS? It's not standard BFS. We don't just iterate. We choose the node that has the minimal weight, greedy. It's a greedy BFS. You choose the greedy BFS next node and you calculate the weight to all its neighboring. But then you move on to the next node on the second layer that we have visited after the first visited node, because we did not finish visiting all the neighboring nodes in the BFS. So yet again in the loop, you look for the neighboring node in the unvisited array, which originally contained all the nodes, all the vertices, and you look for the one which has the minimal weight, and then you apply the Dijkstra algorithm again, which hints like a recursion. We apply the algorithm again in order to find all the minimal weights into the upcoming nodes. And then we look again at all the unvisited nodes, and we choose the node which has the minimal weight. We remove it or mark it as visited on the unvisited, and we move it to the visited array. And again, we apply the algorithm and calculate the minimal weight into all the neighboring nodes. So to sum up, we just have a table which holds the minimal weight or cost into any node from the source single node, and then we choose from the unvisited array the node which has the minimal weight. We remove it from the unvisited because we are now source visiting it. We calculate the weight into all the neighboring node. We choose again the node that has the minimal weight from the unvisited, and we calculate. And this is basically the algorithm of Dijkstra. And this is Dijkstra algorithm. We simply take a source node, we calculate the weight to each of the neighboring nodes, and then we take the next vertex with the minimal weight from the original source node, and we calculate again the weight into all the neighboring nodes, and then we take again from the unvisited array the node with the minimal weight, and we continue calculating the weight to all its neighboring nodes until we finished visiting all the unvisited node. Once we have finished, we know the minimal path from the original source single node into all other nodes, so you can simply know the minimal path. And because in the counting table we have also stored the previous node from each node, then we can actually get the path itself and not just the weight.